Hello, everyone. Welcome back. So today we're going to talk more about compound interest. You've seen in a previous video we did some of the basics. Now we're going to continue on that and do a few more ideas about compound interest. Our goals are to be able to calculate future values based on compound interest. That's something we've already done. And also use logarithms in terms of the time needed to reach a certain future value. That's something that also has already been done. But a few things are new, is be able to find the time required to double or triple initial investment. And we'll see how to do that idea in general. Then also be able to find what's called the annual percentage yield. There's a formula for that, and we'll talk about what that is and how we can find it. Now, so the compound interest formula is reviewing some materials in a previous video. Here's our compound interest formula. And unlike simple interest, this is what's called compound interest. This grows exponentially. And exponential growth is much faster, especially in the long run, than simple interest or linear growth. Now, so here, our P is our principal. That's our initial investment. Our R is our annual interest rate as a decimal. Then M is number of compounding periods per year. T is time in years. So if your time is not given in years, you have to convert it to years. Then A is a future value, or the amount you'll have after T years. Now, this formula can also be written in a simpler way, although it still contains the same information, like this. A is equal to P, then in parentheses 1 plus I to the n, where I is the same as just R over n. It's also known as the interest rate per compounding period. It just simply is R, your interest rate is a decimal, divided by M, your number of compounding periods per year. And then n is the total number of compounding periods. We get that by M times T, the number of compounding periods per year, then times the number of years. Now, the number of compounding periods, if you see annually, that means it's once. Semi-annually is twice a year. Quarterly is 4 times a year. Monthly, as you expect, is 12 times per year. Weekly is 52 times per year. And actually, daily, for many banks, is used as 360 times a year. So that's also what we'll be using for this. So first, let's take a look at a few examples with this formula written this way. So when we come over to the right, number 1. This says find the future value if $1,000 is invested for 3 years at 3% compounded quarterly. Let's write down what we're going to do. So once again, we're going to use this version. A is equal to 1 plus I to the n. Oops, I forgot my P. The P in there. Let me squeeze that in. Okay, for P, that's what our investing. Okay, that's the $1,000. Now it says find the future value. So A is our future value. That's our unknown. Then R, you define I and N. So our interest rate is a decimal, it's 3%. It's going to be 0.03. And then M it's compounded quarterly. So M is 4 times per year. Now, if you notice, of course, I'm just going to be using the I and N here. So now I is R divided by M. So it's going to be 0.03 divided by 4. And do that on your calculator. And this will give the interest per compounding period. And also don't round this off. So this is 0.0075. Or that's going to be if we things in decimal per percent, 0.75% per quarter. Okay, so quarterly, that's how much that's going to be. So 3% per year, then per quarter is about 0.75%. And then our N is going to be our M times T is going to be 4 times 3, which is 12. Okay, so we're going to plug all that in, and let's just make a line here so make sure we can separate this. And say, so what we have then is the future value A is equal to 1,000 times 1 plus 0.0075. That's our I. to the 12th. Now you see this is a much cleaner formula. You can also reduce that to 1,000 times. We just add that to 1.0075 to the 12th. Okay. Now, we're also going to use Desmos to help us out with this. Let's go to Desmos just to calculate these. You can also use it as, if you don't, you want to use that to graph, or not only to graph, but also to calculate things. So 1,000 times 1.0075, then raised to the 12, and we'll see, as it says, that's $1,093.81. $1,093, around the nearest cent, 81 cents. So that's the future value. So what's new here is, once again, this I, which is the interest rate per compounding period. So in this case, it's doing quarterly. It was 3% annually, or 0.75% quarterly. Okay, and then, of course, our N is our total number of compounding periods, which is 12. Compounding 4 times per year for 3 years. Okay, now, another question, possible one similar to this: how long will it take $5,000 to grow to $7,000 if the interest is 9.6% compounded continuously? So let's also review that. There's also a continuous compounding formula. And recall, we also said that continuous compounding is the ultimate compounding. So for everything given the same, you pair all your compounding periods to continuous compounding. Continuous compounding generates the most growth, although there's kind of diminishing returns with each increase. So the amount gained for continuous compounding versus daily compounding is not really that much, but gives you the greatest amount of growth per given interest rate, time, and principal. So let's come over and take a look at this. So how long would it take 5,000? Since let's use our formula. So we're going to have A is equal to P times 1 plus I. I'm sorry, that's not the wrong formula. So this one, we're going to use the continuous compounding formula. Let's go down here, and that, right, for continuous compounding, is that exponential is E to the RT. Let's plug everything in. So we have, of course, A, P, R, and T. Now, since it asks how long it will take, that's going to be the time. That's our unknown. That's our question. So and also the rate is 9.6%. So as a decimal, that's going to be 0.096. Once again, don't round off your rates. Now, you have to decide which one is the principal or starting amount, and which one's the final amount. If you read it, it says how long will it take $5,000 to grow to $7,000. So $7,000 is a future amount, or the time after or the amount after the given time. So that's going to be 7,000 is going to be your final amount or total amount, and then we're starting then with $5,000. Now, so what you can do is let's plug all this in. If we do that, then we're going to have A, which is going to be 7,000, is equal to 5,000 times E to the R, which is 0.096 T. Okay, now we want to solve for T. So let's kind of get everything else on that side. Let's divide both sides by 5,000. And if we do that, then it's going to be 1.4. So what we have is 1.4 is equal to E to the 0.096 T. Now, here, of course, we're solving for T. You want to get T by itself. The way to undo the exponential, specifically this one, is to use logarithms. Specifically, we're going to take the natural log, which is the inverse of this one, of both sides. We do that then, so we're going to have the natural log 1.4, and that's also just a constant, is equal to the natural log of E to the 0.096 T. Now, since the natural log and or inverse of each other, these cancel each other out, and we're left with then is the natural log of 1.4 is equal to 0.096 times t, and then just divide by 0.096 to get t by itself. And then we have that t is equal to just that, the natural log of 1.4 over 0.096. Once again, we use Desmos for this. Now, to find this, let's go look on the keyboard. We have some functions. We'll find that particular function. So we'll scroll down. It should be here. Yeah. So natural log of 1.4, or it gives you that value, but that's not what we want. Then divided by 0.096, and that's our value, about 3.5. So let's round this to 2 decimal places, about 3.50. It's about 3.5. This is going to be given in years, so about 3.50 years. How do we know it's in years? Well, remember, in the formula, we have to put insert our time as years. So in the formula, if we solve for t, we get this in years. So we'll take approximately 3.5 years for $5,000 to grow to $7,000 if invested at that rate, which would be a really high rate. In real life, you're probably going to get that kind of rate for a bank or anything, but for just solving problems purposes, that's what it would take. Okay. Now, next question is kind of interesting. It says, how long will it take a money to double if it's invested 7% compounded daily? Okay. Once again, we're going to use the periodic compounding formula, not continuous. So we're going to use the A is equal to P times 1 plus I to the N. Okay. Now, let's think about what it takes to double. Okay. So if money is double, so the principal. So what this means is that the future value is twice the principal. And the principal is what you put in, what you start with. So if the future value is twice the principal, we can simply write that. What that tells us then that A is going to be 2 times P. Now, if we were also tripling it, it'd be 3 times P, quadrupling it, 4 times P, and so forth. Now, what does this do for us? Well, what this does then is this allows us to replace A with 2 times P is equal to P times 1 plus I to the N. And now we can just cancel out the P's. And what we have then is 2 is equal to 1 plus I to the N. Okay. Now, let's insert some of our values. So what we know then is I is equal to R, the interest rate over the compounding period. And the interest rate was 7%. So this would be 0.07 over the number of compounding periods compounded daily. Remember, daily in this case is going to be 360, not 365. Okay, now this is going to be a small number. We'll have to make sure to carry at least a few significant decimal places. So 0.07 divided by 360. Yeah, so I'm going to write that. That's going to be 0.0030, then 19. I'll stop there. So that's the daily rate as a decimal. They want to change it to percentage, just move your decimal place 2 places to the right. Okay, and of course, N is what we're essentially going to be looking for is the total compounding periods. Okay, now let me actually put some space here. All right, that's our total number of compounding periods. Now, what this is going to be, we're going to plug these in. To do that then to this, we're going to have 2 is equal to 1 plus 0.00019 raised to the n. And of course, that's just going to be 2 is equal to 1.00030 to the n. Now, once again, we want to find n, small n. And we can use logs. Of course, you can use any log you want. Let's use ln again. Take the natural log of both sides. We have natural log of 2 is equal to the natural log of 1.00019 to the n. Okay, now, once again, how does that help us? Well, remembering our rules of logarithms, I can bring this exponent down front, and now I'll have the natural log of 2, or that's just a number. Natural log of 2 is just a number. Then we have n times the natural log of, and I can get rid of the parentheses here, 1.00019. Okay. Now, I also just divide both sides by this. This natural log of this is also just a number. So if I divide both sides by that, I have n is equal to the natural log of 2 divided by the natural log of 1.00019. It's going to use Desmos to help us approximate this. And remember, this gave us the total number of pounding periods. So natural log of 2 divided by the natural log of 1.00019. Let's go back into our functions. Let's go here again. Let me actually, there we go. You can still see that value if you need it. Go back to our functions. So natural log, and then of 2, and it was divided by, once again, the natural log of 1.00019. Now, that's a number of compounding periods. So let's do 3648.49. So 3648.49 if you round to 2 decimal places. 3648.49. 3648.49 compounding periods. Now, that's not that meaningful. Remember, we're compounded daily. So, remember, so n was equal to m times t. And so then t, actually, let me a little more space here. Then t, of course, is going to be equal to, we divide both sides by m, is n over m. And so n is this, 3648.49 divided by m, which is 360 per year. And that will give us our approximate time in years. So I'll just use a calculator for this. So 3648.49 divided by 360. And that comes out to be not 10.13 years, a little over 10 years. So under those conditions, it should take a little over 10 years. So if we read the question again, what did it say? It said, how long will it take money to double if it's vested at 7% compounded daily? Okay. And so it's going to take, on those conditions, a little over 10 years. And also what's interesting about this is with those conditions, it doesn't matter how much I start with. To double it, whether I start with $1 or $10 or $1 million, it's going to take that long to double it at that interest rate, compounding daily. Okay, last topic. And now we want to talk about what's called the, and also increase what increases future value. I've listed this before, but to increase your future value in any of these compound or continuous interest formulas. So if you want to increase what you get in the future, of course, increase your principal, increase what you start with, increase the interest rate. Of course, often that's out of your control. That's what maybe what the bank, to some extent, often what depends on what banks may offer. Increase the time. Okay, the longer it's in there, the more you'll grow. And also increase the number of compounding periods. Once again, continuous compounding is a limit, but also increasing compounding periods has diminishing returns. You'll get more but not a lot more than the next lower number of compounding periods. Okay, last thing is something called the annual percentage yield. And let's read this. It says if a principal amount is invested at an annual, or what's called nominal rate R, compounding M times per year. Actually, let's do a little housekeeping. I should have made that in italics. So this is what's called the annual percentage yield. And what's this is useful for is often good at comparing different rates, because sometimes there are different yields. Yield is how much you're going to get per year. Annual percentage, of course, this says annual per year, percentage yield. And so it's a good way of comparing different rates across different compounding periods. Because as we said, if you increase the interest rate, that increases your amount, your return, your yield. If you increase the number of compounding periods, also increases your yield. But sometimes it'll be hard to compare them as they are. So use something like this to help us compare. Now, so let's take a look at an example and see how this works. An online bank listed a 1-year CD. There's 1.25% compounded monthly. Find the APY as percentage rounded to 3 decimal places. Okay, so here's our formula. Let's write this down. So APY, annual percentage yield, is equal to 1 plus R over M. You also could write I if you want. Then we have M, and we have minus 1. So now we need to figure out what everything is. So, of course, interest rate, 1.25%. So our R is going to be 0.0125. Change that to a decimal, so don't round that off. Our M, is compounded monthly, M is 12. And then, actually, those are only, if you notice, those are our only variables on this side. And so, because that's the only thing that really affects your annual percentage yield. So this just is a way of comparing different rates at different compounding periods. So we plug this in. So APY is going to be equal to 1 plus 0.0125 over 12 raised to the 12 minus 1. Actually, we can write all this in Desmos just as it is, which we can simplify it. But we can actually just type it in like that. Let's see what we get. Then we'll have to convert it to a decimal. Get rid of the keyboard now. And so, in parentheses, we have 1 plus then 0.0125 divided by 12. And make it look just like that. Then raised to the 12th power. Then also make sure we write this like this, minus 1. And what that says is about 0.01257. Okay, so it said it wanted this as basically as a percentage rounded 3 decimal places. So our decimal place, if we change the percentage, is going to be right here after the 1. So 3 decimal places is going to be right here at the 7. So once again, if we change this is a decimal. We change this to a percent, remove the decimal place 2 places to the right. So the 3rd decimal place in a percent is going to be right here at the 7. So the next one is 1, so leave it at that. So 0.01257. Let's make sure this is like a 1 right here. And so this is going to be 1.257%. Okay. Now, if you notice, that's a bit higher than what was stated here because that was a monthly compounding period. Okay. And so this gives your annual percentage yield. So this way is the way you compare it to other rates given for different compounding periods. For example, if you had, if it was compounded daily, you would get, or compounded weekly or daily, you get slightly more than this. Compounded, quarterly, you get less than this. But also, if you're compounding, let's say compounded for a smaller interest rate, maybe 1.2, but compounded weekly, question would be, is that bigger or smaller? Does that give you a better average, a better annual percentage yield, a better return? it's hard to say without doing something like this. This allows us to compare rates, once again, at different different yearly interest rates at different compounding periods. So what we've learned today is more about compound interest, learned a different way to write the formula. Okay, just a more compact way to write the formula. We learned to be able to solve for the time it takes to reach a certain for time it takes for a certain amount to grow to a future value. We also learned how to calculate a doubling time or even a tripling time using the same concept. We also learned about how to find the annual percentage yield, compound interest. Thank you. Have a good day.